Hello students, welcome to EPG Pathshala. I am Dr. Manjula Sharma from University of Delhi. Today we are going to discuss about the module Principles and Instrumentation of the Raman Spectroscopy from the paper Characterization of Materials 1. After studying this module, you should be able to understand the principles of the Raman spectroscopy, the various types of Raman spectroscopy, that is the surface enhanced Raman spectroscopy, tip enhanced Raman spectroscopy, coherent anti-Stokes Raman spectroscopy, simulated Raman spectroscopy, resonance Raman spectroscopy, and confocal Raman spectroscopy, and finally the instrumentation. Raman spectroscopy is an important technique to identify several materials which can be solids, liquids, or gases. It is a simple, non-invasive system and requires no elaborate sample preparation. The sample is irradiated by a monochromatic light and a spectrometer examines the scattered light. This technique works on inelastic scattering of the monochromatic light. During the scattering process, frequency of the incident photons is changed. Photons of incident light are first absorbed and then re-emitted by the sample. Frequency of these re-emitted photons shifts either up or down in respect to the primary monochromatic frequency. The phenomenon is termed as Raman effect. These shifts contain valuable information on the vibrational, rotational, and low frequency transitions of the sample molecules. Raman effect depends on molecular deformations in electric field E influenced by molecular polarizability alpha. Laser beam may be regarded as an oscillating electromagnetic wave with electrical vector E. After interacting with sample, it induces electric dipole moment P, which is equal to alpha E, and deforms the molecules. Due to the periodic deformation, molecules vibrate at characteristic frequency μm. Thus, the monochromatic laser beam having frequency nu0 excites the molecules and converts them to oscillating dipoles. These oscillating dipoles produce light of dissimilar frequencies as revealed in Figure 1. Figure 1 shows the vibrational levels of the material. Students, the molecule without any Raman active modes absorbs a photon of frequency nu0. The excited molecule comes back to its fundamental vibrational state after emitting light of same frequency nu0. This phenomenon is described as the elastic scattering. A Raman active molecule in its fundamental vibrational state absorbs a photon. Some of the photon's energy is transmitted to molecule with frequency nu-m, decreasing the frequency of scattered light to nu0 minus nu-m. This Raman frequency is known as Stokes frequency or simply Stokes. The molecule absorbing the photon is already in its excited vibrational state. Excessive energy of excited Raman active mode is released. The molecule comes back to its fundamental vibrational state and the frequency of scattered light increases to nu0 plus nu-m. This Raman frequency is called anti-Stokes frequency or just anti-Stokes. Raman shift is independent of the incident light frequency. It is the characteristic feature of material undergoing Raman shift. The shift delta nu is positive for Stokes and negative for anti-Stokes. From figure 1, it is seen that the shift in Stokes as well as in anti-Stokes line with respect to the Rayleigh line is equal. This happens since both cases involve the gain and loss of one vibrational quantum of energy or same amount of energy. Moreover, the intensity of anti-Stokes line is lower than that of the Stokes line. This is because anti-Stokes line is caused by molecules which are vibrationally excited, very less in numbers, before irradiation. Thus, in Raman investigation, more intense Stokes line is usually recorded. Infrared or the IR absorption spectroscopy is the other vibrational method to study molecular structures. However, it diverges from Raman spectroscopy in the manner of molecular transitions. For transitions to be Raman active, the polarizability of molecule should vary during vibration, thereby necessitating change in position of molecules electron cloud. Whereas for infrared transitions, molecules undergo changes in dipole moment during vibration. Homonuclear diatomic molecules, including hydrogen, nitrogen, oxygen, etc., that do not exhibit infrared spectra due to absence of permanent dipole moment, are Raman active because their vibration is associated with variation in molecules' polarizability. Therefore, Raman spectroscopy allows examination of vibrational spectra of compounds which cannot be studied by IR absorption spectroscopy. Raman spectroscopy is invariably employed for gases, liquids, and solids, thereby lending it an extremely versatile tool for examining diverse materials. Raman spectrum is characteristic to materials being studied due to their distinct structural arrangements. Therefore, the composition of unknown substances can be easily determined. This renders Raman spectroscopy best for qualitative examination of substances. Students, now let us see the different types of Raman spectroscopy. First, the surface enhanced Raman spectroscopy or SERS. Surface enhanced Raman spectroscopy or SERS is one of the most sensitive devices which are used for highly sensitive structural detection of analytes in low concentrations. This is achieved by amplifying the electromagnetic fields produced by the excitation of localized surface plasmons (LSP) of adsorbate molecules on the roughened metal surface. While the signals obtained by normal Raman scattering is usually weak, SERS can detect very low concentration of the analytes because of the large increase of the Raman cross-section of an analyte up to 15 orders of magnitude in comparison to normal Raman scattering. Figure 2 is a sketch that presents the main parts and components of surface enhanced Raman scattering device. Colloidal metals and roughened metal electrodes are SERS active surfaces. Colloidal metal is easy to prepare as well as characterize because of its morphology and size. Even though it usually shows a relatively strong activity for the adsorbed molecules, it has poor reproducibility of their properties because it is difficult to control its size. Another type of metal surfaces was tested after that, like gold and copper. All those metal surfaces increased the intensity of Raman signal up to 104 to 106 fold. In general, silver and gold substrate are the most often used types because they are the most air-stable materials. Copper, on the other hand, is more reactive with air, which will affect the success of SERS. SERS substrates become available in various shapes and coating after advanced development. Different concepts have been developed to enhance the fabrication of SERS substrates using bottom-up and top-down approaches. The most important thing to realize to improve SERS is to provide the industry with most sensitive, cheaper components for the structure of the spectroscopy and simpler fabrication method. Students, now let us see the second type of Raman spectroscopy, that is the tip enhanced Raman spectroscopy or TERS. Many research interests require Raman imaging of a small area within the sample. However, conventional Raman technique can be misleading in some cases due to the masked signal contribution by the surrounding area signals. Such issues encouraged further research on Raman scattering enhancement. Tip enhanced Raman spectroscopy or TERS is a powerful solution that combines between two techniques, that is the scanning probe microscopy and Raman spectroscopy. TERS can provide a topographical and spectral or chemical information simultaneously using SPM and Raman respectively. TERS has similar instrumentation, material requirement, and enhancement principle as SERS, but by using a metal tip or metal nanoparticle instead of the metal film, TERS technique involves bringing a metal tip or a metal nanoparticle very close to the sample, that is, with a nanometer distance. An excitation laser beam will illuminate the tip apex, creating an enhanced and confined electric field zone. This localized field will result in enhanced scattered light from the sample located under the tip. A diagram of TERS concept can be seen in figure 3. The mechanism behind TERS ability to enhance the electromagnetic field at a tightly focused spot can be attributed to surface plasmon resonance and electrostatic lighting rod effect. Figure 3 shows the tip enhanced Raman spectroscopy concept. Students, there are mainly three scanning probe microscopy modes that are used in TERS experiments. The most commonly used is the atomic force microscopy. The other two SPM modes are shear force microscopy and scanning tunneling microscopy. As can be seen in figure 4, the tip can be illuminated in three ways: the bottom or backlit reflection illumination, side illumination, and top illumination. The bottom illumination works for transparent or very thin film sample, while the other two are used also for opaque samples. Each of these illumination techniques has its own limitations and advantages. The selection is mainly based on the analyzed sample and the SPM modes. Figure 4 shows the diagram showing optical alignment setup in TERS. A is the bottom illumination, B shows the side illumination, and C shows the top illumination. Now, let us see the third type of Raman spectroscopy, which is called as the coherent anti-Stokes Raman spectroscopy, or CARS. CARS is a non-linear Raman technique that is used to enhance the Raman signal. As the name indicates, it uses coherent laser beams to generate a signal with frequency higher than the excitation frequency. Thus, it is regarded as anti-Stoke frequency technique. The main principle of this technique is based on using multiple excitation laser sources. It involves pump coherent monochromatic field at frequency of omega p and Stoke excitation field at frequency of omega s, overlapping spatially and temporally. When the incident light is focused on the sample at a small focal volume and probed by a third laser beam, a strong anti-Stoke Raman signal is created at blue shifted frequency away from fluorescence effects and in the face of matching direction. A strong signal is created with frequency of omega as is equal to 2 omega p minus omega s, when the difference in the frequency of the incident light delta omega is equal to omega p minus omega s is tuned to the Raman active molecular vibration of the sample, that is omega vibration. Hence, CARS provides information about the intrinsic vibrational bond of the sample with three-dimensional resolutions. Since CARS is a four-wave mixing process, the signal has a quadratic dependence on the incident radiation, unlike the spontaneous Raman signal, which has linear dependence on the incident field intensity. Figure 5 indicates the diagram of CARS energy levels. Now, students, let us see the stimulated Raman spectroscopy, or SRS. SRS is another nonlinear process, stands for simulated Raman spectroscopy. The basic principle of this coherent phenomena is based on the incident of two photons, pump and stoke, like CARS principle. The two laser beams coincide on the sample. When the frequency difference matches the molecular vibration frequency of a bond in the target molecule, this will induce simulated excitation in the vibrational transition. Consequently, this will result in Stoke field amplification, where the intensity of the Stoke experiences a gain, and pump field attenuation, where the pump intensity experiences a loss termed as stimulated Raman gain and stimulated Raman loss respectively. It should be mentioned that SRS is not identical to CARS, although both are coherent phenomena that are based on two incident photons. The SRS does not have a signal at frequencies other than the excitation wavelength. Another difference is that SRS has a linear dependence on concentration, and the resulting spectra match with spontaneous Raman spectroscopy, making interpretation much easier than CARS. Also, the SRL and SRG only occur if the frequency difference matches a molecular resonance. Simulated Raman spectroscopy as a coherent Raman technique allows an enhanced real-time imaging, overcoming the low signal intensity of spontaneous Raman spectroscopy and improving signal to noise ratio. Additionally, the photon flux is directed collinearly with the probe laser. That means that SRS are not sensitive to the background fluorescence, since only a small fraction of this fluorescence is emitted collinearly with the probe. Students, now let us see The fifth type of Raman spectroscopy, that is the resonance Raman spectroscopy or RRS. Resonance Raman spectroscopy is an instrument which measures the shift in the frequency of the photon when the energy of photons from the incident light is approximately similar to the energy needed for electronic transition. The resonance excitation can increase the oscillation charge displacement of electrons. As a result, it will increase the induced dipole moment, which will directly enhance the efficiency of Raman scattering. The enhancement factor of resonance Raman scattering compared with normal Raman can be high as 108. It is important to note that fluorescence is more likely to interfere with resonance Raman more than non-resonance scattering. Fluorescence is one of the challenges that limit the applicability of Raman technique. It was found that using UV resonance Raman spectroscopy for characterization of catalyst reactions and synthesis can eliminate the fluorescence effect. Most of the catalysts showed fluorescence spectra within the visible region, so shifting the excitation laser to the UV region, where lambda is less than 300 nanometer, will help to avoid interferences. Resonance Raman spectroscopy can be used to study the structure of hemiprotein and the function of human body cell. It can help to determine the shapes of potential surfaces or molecular geometries in excited states. Next is the confocal Raman microscopy. The probe head in confocal Raman microscopy work on focusing laser light onto the sample by using a microscope objective, and the pinhole will refocus the backscattered Raman signal, which makes it to behave as a spatial filter. After that, the signal will be collected on a CCD detector to create a spectrum. Depth profiling with confocal Raman microscopy can be applied in two ways. The first approach uses plotting of intensity of a specific band as a function of the distance from the sample surface. This provides information about the composition and structure of gradients of the sample. The second way is to acquire a pure spectrum of buried structures and used to identify determinations. This type of Raman microscope has proven to be a useful analytical technique. It showed a set of advantages such as high spatial resolution, clear image quality. In addition, the sample needs no preparation. Now, let us see the instrumentation. Either dispersive or non-dispersive spectrophotometers can be used. A prism or a grating is employed in the dispersive spectrophotometer, whereas non-dispersive is employed in the interferometers, analogous to Michelson interferometer in FTIR. Fundamental components of Raman spectrophotometer are: first, the excitation source, that is laser. Early Raman spectrometers employed mercury arc lamps, where a 435.8 nanometer line of coiled low pressure mercury arc lamp was used as light source until 1960s. Laser sources became available in late 1960s and completely replaced the mercury lamp. These laser sources provide stable and intense beam of radiation. There are a variety of lasers which can be used. For example, argon ion having 488 and 514.5 nanometer, krypton ion having 530.9 and 647.1 nanometer, helium neon, that is 630.8 nanometer, near infrared diode lasers, neodymium yttrium aluminum garnet, that is NdYAG, and ND orthovanadate, etc. Short wavelength sources, for example argon ion and krypton ion lasers, generate considerable fluorescence and result in photodecomposition of the specimen, while long wavelength sources For example, diode or NDR lasers can operate at very high power without decomposing the sample and also eliminate or reduce fluorescence. Second is the optics for sample illumination and light collection. Light from the irradiated or illuminated spot is collimated by a lens and guided to interference filter or spectrometer to get Raman spectrum. Third is the wavelength selector or the filter or spectrometer. Bandpass filters are used to isolate a single laser beam. A combination of notch filter and high quality grating monochromator is mostly employed in dispersive instruments. Double or even triple grating monochromators, super notch filters, rejection filters, holographic notch or edge filters, and holographic filters are used to separate relatively weak Raman lines from intense Rayleigh scattered radiations. Fourth is the detector, which consists of photodiode array CCD or PMT. Thermoelectrically cooled PMT and photodiode array detectors were used in early models of dispersive Raman spectrophotometers. Advances in instrumentation and technology replaced these detectors with more sensitive charged transfer devices such as CCDs and CIDs. These devices act as a detector and used in the form of arrays. In CTD arrays, photosite converts the incoming optical signal into charge which is integrated and transferred to readout devices. Multi-channel CCD detectors are used with laser wavelengths of less than 1 micron, while single-element low-bandgap semiconductors such as germanium or indium gallium arsenide detectors are used with laser wavelengths of greater than 1 micrometer. Figure 6 shows the schematic of Raman spectrometer. The sample is irradiated with a laser beam. Light from the irradiated illuminated spot is collimated by a lens and guided to interference filter or spectrometer to get Raman spectrum. Wavelengths near laser line corresponding to elastic Rayleigh scattering are filtered out and remaining collected light is dispersed on a detector. Spontaneous Raman signal is generally very weak since majority of incident photons suffer elastic Rayleigh scattering. Thus, special methods are undertaken to separate it from the dominant Rayleigh scattering. Instruments like tunable and notch filters are employed to minimize Rayleigh scattering and acquire good Raman spectra. So, students, let us summarize what we have learned in this module. We learned the principle of the Raman spectroscopy. Then we discussed the different types of Raman spectroscopy, that is, the surface enhanced Raman spectroscopy, the tip enhanced Raman spectroscopy, coherent anti-Stokes Raman spectroscopy, the stimulated Raman spectroscopy, resonance Raman spectroscopy, confocal Raman microscopy, and towards the end, we studied the instrumentation of Raman spectrometer. Thank you.